law of mass action and equilibrium constant K equilibrium in terms of concentration Kc, in terms of partial pressures of reactants Kp, and in terms of mole fractions of reactants and products Kx. Okay, now consider the reaction A times A plus B times B is in equilibrium with C times C and D times D. Now, according to law of mass action, rate of forward reaction is directly proportional to the concentrations of reactants. Concentration of reactant A raised to small a, B raised to small b, and rate of backward reaction or reverse reaction is Rb, directly proportional to the concentration of C, product C raised to small c, into concentration of product D raised to small d. Now, rate of Rf and Rb are rates of forward and rate of backward reaction. Rf and Rb are rate of forward and backward reaction or reverse reaction. So, rate of forward reaction, that is Rf, is equal to Kf into concentration of A raised to A into concentration of B raised to B. For reverse reaction or backward reaction, rate of backward reaction Rb is equal to Kb into concentration of C raised to C into concentration of B raised to D raised to D. Okay, where the Kf and Kb proportionality constants are rate constants of forward reaction, that is Kf, and rate constant of backward reaction, that is Kb. Now, at equilibrium, rate of forward reaction becomes equal to rate of reverse reaction. Rate of forward is equal to rate of backward reaction. Okay, so Rf is equal to Rb. Now, as Rf is equal to Rb, rate of forward reaction and rate of backward reaction becomes equal. From this relations, we can write Kf into concentration of A raised to A, B raised to B is equal to Kb, C raised to C, D raised to D. Okay, now rearranging, moving the Kb on left hand side and concentration terms on right hand side, we get Kf upon Kb is equal to C raised to C, D raised to D upon A raised to A, B raised to B. This is the ratio of Kf to Kb is called the equilibrium constant, and this equilibrium constants is in terms of concentration terms, so we can also write Kc. Okay, so Kc is equilibrium constant in terms of concentrations. Okay, you can see here product concentrations divided by reactant concentrations, and the powers are coefficients in balanced chemical equation. So this equation number 1 is called the law of chemical equilibrium. Now let's see the relationship between Kp and Kc. Kp is the equilibrium constant in terms of partial pressures of the reactants. Okay, now Kp is equal to, instead of concentration, write down the partial pressures of C raised to C, partial pressure of D raised to D, partial pressure of A raised to A, and partial pressure of B raised to B. Okay, now we already know that the ideal gas equation is PV is equal to nRT. So P is equal to N by V RT, and N by V is nothing but the concentration, amount per volume, that is mole per liter, which is nothing but the concentration. N by V is concentration. So P is equal to CRT. So replace all P terms by CRT. So Kp is equal to concentration of C RT raised to C, D RT raised to D, A RT raised to A, and B RT raised to B. Okay, so we can take out the concentration terms here. C raised to C, D raised to D divided by A raised to A, B raised to B into RT raised to C plus D minus A plus B. Okay, but we know that this is nothing but the Kc. So Kp is equal to Kc into RT raised to delta N, where delta N is C plus D minus A plus B. Okay, the change in number of gaseous molecules. Here C plus D are number of gaseous products and A plus B are number of gaseous reactants. So delta N, replace C plus D minus A plus B by delta n. This is the relationship between Kp and Kc. Kp is equal to Kc into RT raised to delta n. You have to put here bracket RT whole raised to delta n. Okay. Now relationship between Kp and Kx. Now Kx, equilibrium constant in terms of mole fraction. Replace all the concentrations or partial pressure terms by mole fractions. So equilibrium constant is equal to product of products, maybe concentration of products or partial pressures of product or mole fractions of products. Here mole fractions of products divided by mole fractions of reactants. So xc raised to small c, xd raised to small d divided by xa raised to small a, xb raised to small b. Now according to Dalton's law of partial pressure, we know that partial pressure exerted by reactant A is equal to mole fraction of A into P total. Similar for Pb, xb into P. For partial pressure of C is xcp, partial pressure of D is xdp. Okay. Now write down the Kp. Kp is equal to partial pressure of C raised to C, that is xcp raised to C, into partial pressure. You can see the equation. Equation number 2. Okay. Partial pressure of C into partial pressure of D, C raised to C, partial pressure of D raised to D divided by partial pressure of A raised to A and partial pressure of B raised to B. So instead of partial pressure, you can write, instead of PA, you can write XAP, XBP, XCP, XDP. Okay. So XCP raised to C into XDP raised to D divided by XAP raised to A and XBP raised to B is equal to, now take out the mole fraction terms on one side, xc raised to C, xd raised to D divided by xa raised to A, xb raised to B into pressure raised to C plus D minus A plus B, which is nothing but the delta n, and this is the equilibrium constant in terms of mole fractions, Kx. So is equal to Kx P raised to delta n. Therefore Kp is equal to Kx into P raised to delta n. So the relationships between Kp and Kc is Kc RT raised to delta n, which is nothing but the Kx P raised to delta n. Okay. And when delta n is equal to 0, RT raised to 0 become 1, so Kp is equal to Kc, and P raised to 0 become 1, so Kp is equal to Kx. So Kp is equal to Kc is equal to Kx when delta n is equal to 0, because RT raised to delta n raised to 0 becomes 1 and P raised to 0 also becomes 1. That's why Kp, Kc and Kx are same. But then when delta n is non-zero, the values of Kp, Kc and Kx are different. Okay. Here is the relation. Kp is equal to Kc RT raised to delta n, Kp is equal to Kx P raised to delta n. So Kc RT raised to delta n is equal to Kx P raised to delta n.